we roll back. Some rock, some wind, some 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 roll back.
Hi, my name is Loris Crow, and we are executing a showtime. Zig Showtime is the show where members of the Zig community come on stream to share coded ideas with the broader public. Every episode features two speakers who will present and take questions from you, the viewers. Zig Showtime is not just what you're seeing on the live stream, but also the discussions that you can have while watching, and that's why I encourage you to join one of the existing Zig communities that you can find by going to ziglang.org. Well, hello! Episode number 10. So we are to double digits, if you like base 10. News, well, I think the most recent news is still the newsletter. I think I'll try to push it for a little bit more in the introduction of Showtime. So if you want to be updated when a new Showtime airs, but you don't like notification emails from Twitch, which can be spammy, and especially sometimes I start streaming, but I'm not streaming Showtime. I'm just live coding. So if you don't want those, and if you don't like Twitter either, then check out the newsletter. You can give your email address and you will receive emails. Otherwise, there's RSS, or you can also check it out just by going to the archive, which is available online. Just go to zig.show, then click the newsletter button, and you'll find everything. Another thing is that I noticed that Twitter doesn't give much space to properly give an introduction to for new talks. So I'm using the newsletter also as a way to have more space to say more things, get slightly more into detail. Don't expect anything crazy, but like at that point, I don't have only a limited number of characters to introduce two different talks. So you saw what we have on the plate for today, and so let's move directly into the first talk. So let me put up the title. Yep. Okay, so Alex is a returning speaker, and last time he gave a talk alongside August on ZLS, the Zig language server, which is considered an invaluable tool by many Zig programmers. Since then, Alex has become part of the core development team, and let's not forget, all of this while working as a civil engineer in Greece instead of handcrafting pre-processed CSS in a food review startup in Silicon Valley while sitting in a Starbucks and sipping on a pumpkin spice latte. Well, the title is a practical guide to compile time evaluation. So, Alex, the stream is yours.
Thank you very much for the kind intro. So today we are going to be talking about compile time evaluation in the Zig language, also known as comp time. The goal of this talk is to introduce some of you to some of the more advanced features and the semantics of comp time, and how you can use it not just to build generic types, but in general to do more interesting stuff. So first off, we will start with one of the core differences between runtime code and compile time code in the Zig language. In compile time, every value has a static lifetime. This means that it is valid forever. It cannot go out of scope and be destroyed. It's very useful to think of this as garbage collection, although this is not true in the current compiler. Here we can see some examples of this behavior. For example, we are defining a function that is returning a reference to a buffer. And this is completely fine at compile time as opposed to runtime code. And of course, Here we can see the same thing. We are taking references to variables that are defined in this function, and this is completely fine. So this is one of the core things that you have to keep in mind when working with compile time code. In addition to this, at compile time, one of the most useful features that can be used for a lot of purposes is slice concatenation. Here we have a simple example. We are defining a string of Unicode count points, and down here we are concatenating some U21 character. Of course, you should try to keep this at a minimum, because every time you concatenate, a new value is created, so some more memory will be used by the compiler. If you know the size ahead of time, it is better to define some array and just use the indexing and etc. But this feature is very useful, especially since allocators cannot be used at compile time, at least for most purposes. So this is some way to have, let's say, some array list type of construct without using allocator. The next feature I would like to talk about, which is relatively new and pretty obscure, is anytype fields. So you can actually define a field in a container type as anytype, and this makes the type of the field variable as well as its value, as always. This is a simple example. We are defining struct, which has an anytype field. And as you can see, here we are concatenating tuples, so the type of the tuple is actually changing. This is not a slice, so the type itself is changing. And this example is just taking a tuple that will be passed to a format function and intercepting some Unicode code points and encoding them as UTF-8. So you can see how this is quite useful. If we didn't have this feature, to do something similar, you would need to probably create some recursive function that constructs a tuple and adds an element every time. But here we can just use iterative style and not worry about recursion at all. So one of the most important features that Zig offers is the type info built-in. This built-in takes a type and returns a description of this type, which is a type info value of the type stud built-in type info. And we also provide some helper function in the stud meta module to help out and reduce a lot of the boilerplate. This is something that you can see in most metaprogramming applications. It is very common to use type info to do introspection and compile time reflection. This is a very simple example where we are extracting some information from a function type. Here we are extracting the calling convention as well as the return type, which can be null, and the type of the first argument of the function. So you can see that this could be a little verbose. Here it's okay because we are doing relatively simple things, but the stud meta module provides a lot of tools to make this, some more complicated things way clearer. For example, here we are using the trait submodule of student meta. We are checking if the type passed in is a struct with this very simple line. And we are iterating over the declarations and checking some stuff. And the same thing for the fields. These functions work with any container type, not just structures, but also unions. And I think enums for some of the functions where it makes sense. You can see that we are very simply unpacking an optional type if the type is indeed optional. And this is very clear and very nice. So in addition to type info, we provide the type built-in, which is exactly the inverse operation. So given a type info value, type will construct a type and return it. This feature has been recently extended to support structured types, or just structures with fields and no declarations. But this opens up a lot of cool things you can do at compile time. For example, you could parse some text, some format, and create a structure that corresponds to the domain-specific language that you have defined. This is a very simple example from a recent pull request. This has not been merged into master, but it is very nice for illustration purposes. This is a function that takes an iterable of types, so this could be a tuple with types, or a slice of types, or an array or a pointer to an array of types. And you can see that we are defining the tuple fields. We want to return a tuple type of the types passed in. So we are defining the fields and iterating over the types. We just give the names that we need, like for a tuple, the names of the fields should be 0, 1, etc. We don't have a default value, they are not complained. And here we are just calling the type built-in. And we are creating a struct and returning this type. So this is very nice, clear, and you can see how powerful this can be, since you can write arbitrary code here and deal with strings or embed some file and do some computations. This is just a very simple illustration, but it is very useful. Okay, so this one is a bit different. So this is a feature that varies a lot between runtime and comptime code. So first of all, let's explain what peer type resolution is. So when you have an expression like an if-else expression, or a switch expression, or even catch or else, etc., the compiler will take all the possible values that can be returned from the expression and find a common type which can represent all the values that are returned. So for example, you could have an if-else that returns either usize or a comptime int, and the common type will be a usize because comptime int can coerce to usize. Now, this does not happen in compile time. In a lot of cases, this is very surprising behavior when you see it for the first time. It's probably a bug that will be fixed in the future, but it is important to keep it in mind in case you're writing code that works both at compile time and runtime. So let's see an example of this. This is actually a bug from the standard library, which has been fixed, but it illustrates nicely what happens. So this is in a standard format, and the code is looking into the options to see if an alignment has been specified, or it uses left aligned as a default. Now, in runtime code, this option alignment field is of type optional alignment. So, and this is an enum literal, so it can coerce to alignment. And the type of alignment is alignment with a capital A. In comp time, when this is null, then the type of alignment will be enum literal. It won't be alignment. So the code switched on an alignment and tried to do some stuff, and this failed because the type was not an enum but an enum literal. And here's the fix, very easy. You must specify the type directly, and everything works fine. But it's very tricky when you first see it. So yeah, keep that in mind. Here's a very fun use of this bug. So this code Andrew wrote in this issue, which takes advantage of this semantics and can actually detect if we are in a comp time context or in a runtime context. As you can see, you can do this very easily by just returning a different type in an if expression and checking what the final type is. So yes, of course, you shouldn't rely on this. This is totally wrong. Please don't quote me. But, it's just to show you a semantic difference between runtime and comp time, and that's it. You should just know about it if you're writing comp time. One last hack that we can do at comp time is what we call comp time closures. So this is a way to capture some comp time mutable state and to modify it through method calls or associate it with some object. You will see in the next slide, it will be clearer. This relies on using anonymous struct literals to avoid caching of functions, because the anonymous struct literals have different types every time they are created. In my experience, this can be pretty buggy in more complex cases, so I would probably avoid doing this, and it may be removed in the future, although it's not sure. There are some proposals that could make this type of code a lot clearer, but none of them are accepted. So for now, this is something that you can do. So this example from Zorro, which is a borrow checker written in comp time Zig. So here you can see we are creating some state, comp time state, which is captured in the struct that is returned by this function. And we are using this unique argument to avoid caching the read function, and we can have access to the state and modify it if we need to. This is just one part. So here is the second part. So here we are doing the same thing. The second argument of this function is also used to avoid caching, so that we get a unique instance of borrows and mute borrows, even if we pass the same t, same type. And we're doing the same trick here and returning the type we saw before. And here you can see how you can use this, and it works, but it's not the most elegant thing. So this was an overview of some compiler features. Thank you very much for listening, and please, if you have any questions, I can answer.
Okay. Thank you very much, Alex. Let's switch to the Q&A view. So, whoa, that was a lot of like very detailed information about how CompTime works. I think I also encountered the pure type resolution thing while writing my Redis client in the past. Thank you for explaining how everything works. I always just assumed it was like random bug in the compiler or something like that. But I see. Well, it is surprising. I agree. It's not a showstopper, though, right? I mean, you just have to pin down what the expected type should be, and everything works out.
Yes, you just have to be a little careful.
Mm-hmm.
But it's surprising for sure.
Okay. Let me see. So while people start typing down questions, let me see if there's a question that I can ask you to start. So I asked you already about how you started with Zig. So when are you going to start programming professionally?
I don't know. As soon as possible, I guess. But yes, I can't give you an answer to this right now.
I see. Well, I mean, my point is, it seems like you're pretty good at programming. So I have no idea how expert you are as a civil engineer. We can assume you are, but I mean, unless you are a super civil engineer, no, not really. Then okay, then you should totally find a way of switching careers. Okay, so first question from Matt Knight: did I see a cat? Is your cat with you now? I saw. Yeah, I also saw it.
Yes, she went away, but yeah, she was annoying.
Okay, so first serious question. So what plans do you have to utilize CompTime for?
So I actually use CompTime in a couple of libraries that I use already, that I have written already. One of them is interface.zig, which is a way of implementing dynamic dispatch in Zig. And I use it to actually take some vtable type and automatically fill it from an implementation type. So some of the code earlier is actually from that library.
Mm-hmm. Let me make it bigger. Okay.
Yes, for example, here you can see I'm checking if the vtable type is correct. I also have written a compile time regex library, which takes the regex and a statically known regex and pretty much compiles it, well, at compile time. And it can match at runtime or compile time, but it is very much a work in progress. But of course, there are 1,000 applications I could think of. For example, I was thinking of implementing a protobuf. In compile time, you could take a protobuf file and create the structures, parse the file, find out what structure you can make, etc. Yes,
Mm-hmm.
you can do a lot of it.
Okay. Let me see other questions. Actually, let me first make you big again. Okay. There's a question from Andrew. Let me see. There's another one. Okay, this one is from Joachim Schmidt. Do you think CompTime is strong enough for a maybe Rust-like borrow checker to be implemented?
So the code I showed actually implements a borrow checker. This is half of the code. You can also write the mutable borrow stuff. But of course, the usage is a little iffy. Like the user must call the correct functions, etc. So you can't automatically just when taking a reference of the value, just check the borrowing. You have to call functions, etc. So it is possible, totally possible, but it's not. It won't be as nice as Rust.
Mm-hmm. So basically, the complete memory safety utopia only works under some kind of authoritarian regime where, right? So like this, the user might, like the programmer might forget to go through the borrow checker thing, and they could still
Right, or they can just access the value itself and do whatever. Obviously, is not possible.
Yeah, but in any case, so go check out Zorro. So if you want to see it in action and see how it works. Okay, there's a question from Andrew that I also kind of wanted to ask, but the way I was about to ask it was a bit more, it was less impartial, I think, than him. So I'll just say his version. So, do you think we should allow declarations like decals in type and close issue 130?
So personally, yes, I would love it. And there are a couple of reasons. Like obviously, it will make it will allow a lot of new things. For example, you could actually implement C import in user space, like embedding a .h file, the parsing it, and creating a struct with the correct decals or stuff like that. Obviously, can make things a little more unclear, I guess, but I don't. I don't think it's so much different than just allowing fields. If we can create fields programmatically, then we have already lost some clarity, if you will. You can just look at a struct, so I don't see why we should restrict type to just allow fields. But
Okay.
that's just my opinion.
About issue 130, do you know which one it is?
I don't
Do you
know
remember?
off the top
Okay,
of my
because
head.
Andrew just said issue 130 is the proposal to have any vtable language feature.
To have, sorry, what?
Vtable language feature. Well, if you are opening it, just open it and.
Right. Personally, I don't think this is necessary. I believe we can write this as a library and be even more flexible than other languages. For example, in Rust or in most languages, the way this feature is implemented is by using fat pointers. So you have one pointer to the vtable and a pointer to the implementation data. But of course, this is just arbitrary and you are locked into it. While using a library, you can do stuff like have different policies for how the vtable is stored and how the object is stored. So you can have, for example, some inline buffer of n bytes and store the object directly there, and avoid one indirection, etc. And I think it's more flexible as a library. Of course, it's a bit uglier, but I don't know. I think it's good enough.
Mm-hmm. Um, So we have another question, but I think let me ask one first. So I think I remember Andrew saying something about one good reason for limiting slightly the power of type was so that instead of generating a bunch of machinery at compile time, the alternative would be to have some kind of step where you write down a Zig file programmatically, right? So you have the first step that creates a Zig file, and then gets added to like a build step. Now, and I think one reason that he mentioned was because that way it will be easier for certain type of tooling to reason about this stuff. Now, one question about like tools like ZLS, or let's just say ZLS precisely. I don't know what the current situation is, but let's say, I don't know, a few years from now, assuming we have Z 1.0, is it reasonable to expect to have ZLS have basically a comp time running inside of it and being able to give out information about what the resulting state of running the comp time step is?
So I think this will be possible. And the way this would be implemented would actually be by running the compiler itself and using the internal information from the compiler, or by implementing some semantic server in the compiler. Without the compiler, this is extremely difficult. You basically have to re-implement a big chunk of the compiler. So ideally, the compiler would just support some program like ZLS or some other program would be a bridge in the compiler and the editor. And I think this is actually planned.
Okay, I see. Makes sense. By the way, for what it's worth, I'm almost of the opinion that not limiting type is the better choice. But I'll say one thing in favor of what I said earlier about the having a step where you write down in a zip file. You write programmatically into a zip file. Like Go also has this approach. I'm not a big fan of it. I think it's clunky. But one big upside, at least of that being a possibility, is that way you can easily inspect what the result of like a, let's say, user space import is. Because if you don't have that step, then everything is somehow in the comp times memory, and it's harder to inspect. You can just scroll through it unless you have adequate tooling. So there's also that.
Yes, I completely agree, but in my opinion, the answer is to create tooling instead of.
Well, Andrew just mentioned, think about stack traces too.
Yes, I see what.
So
I guess it could get ugly.
I guess the answer, we want both. We want everything. No, I don't know. But anyway, food for thought. So the final question then, which I think we kind of answered at least partially with the comp time in ZLS question. The question is regarding to the comp time protobuf generator idea. Love it. Will ZLS be able to understand it, and will you be able to jump to definition, etc.?
No way. This is way too complicated for ZLS in its current state, at least. At the moment, the only comp time evaluation ZLS does is very simple generic types, or not very simple, but generic types, for example, array list or whatever. It can resolve what struct is returned and the type that you passed in as a parameter. But this is it. It can't do anything. It can't evaluate switches or if expressions or anything like that. For now, the tooling is lacking for sure for this kind of metaprogramming approach. But yeah, I think in the future we will have adequate tools to inspect the results.
Okay.
help you out.
Yeah, I think this is a very interesting topic. I mean, I guess everybody loves metaprogramming. It is kind of addictive, and we have in our hands a somewhat unique metaprogramming tool. But metaprogramming can also go wrong, go very wrong. I'm sure everybody has experienced something like that. Of course, most of the time it's macros. But even without macros, it can also go wrong.
Yeah.
Okay, so let me see if there's any other questions somewhere else, but I think we are good. Yes, we are. So, Alex, I think I lost your webcam. Are you still alive? Alex? Ooh. Alex, can you hear me?
I can hear you now. Sorry.
Okay, we lost connection for a moment. Not a big deal. Okay, so any final statement that you want to make before we move forward?
Not really. Like, thank you for having me, of course, and everyone for watching, and have fun in your talk.
Thank you very much. Okay, so we are now going into the break, 10-minute break. But don't go away, because the next talk is gonna be about. It's gonna be for everybody. It's gonna be about the basics of numeric types in Zig for the first half, and for the second half, a bit more spicy, rant about corner cases. So see you soon. Okay, we're back. So, I hope you're ready. Fair warning first. I have 60 slides, so we have to go through it at a good pace. Otherwise, you're going to be here for a long time. Again, as I said earlier, this talk it's 2 talks in one, let's say. The first part is the basics, so it's interesting for people that are new to Zig, less interesting if you already know your way around programming in Zig. And the second part is about an interesting corner case, and it's interesting for people that are active in the community and that know what's hidden in the GitHub issues. So let's get started. This, I think, was my first loop that I wrote in Zig or something like that. Well, at the time, there wasn't a std-debug print. So this is a reenactment, say it's not the original code, but the idea was, I just want to have a while loop, so I set up my indexing variable and just go iterate over it. But if you program Zig, you know there's something missing here, there's something wrong. And if you actually try to run it, it doesn't run, it doesn't even compile because there's a compile error. And the compile error is that, what the error message that you get is variable of type comptime int must be const or comptime, which is kind of a confusing error a little bit. But here's the idea. If you come from like Python or other languages, you're not used to have to specify the size of your numbers, but in Zig, sometimes you kind of have to. And to be precise, there's a kind of a big difference between comp time and runtime. So the error there is not just say something like, what are you doing? This is completely wrong. It's thinking that I'm trying to do something at comp time, while in fact, that was supposed to be something that happens at runtime. And in comp time Zig is kind of like Python. Like in Python, you create a variable and it can hold any number arbitrarily big, and you don't have to care about like the size. But in runtime Zig, you kind of have to. And I say runtime Zig with a star because it's not exactly runtime Zig, but it's well, we'll get to that in the next slide. So this is actually one way of fixing it. You write colon and then the type U64. It's a reasonable choice, not necessarily the right one every time, but that's how you're supposed to write your numbers most of the time. Now, why is this like that? Well, comp time is kind of self-aware. As I said, it's kind of like Python, so it can do some of the things that you can also do in Python. Well, if you were here earlier, you just saw Alex talk where he showed how much introspection you can do around types and everything else. But all this stuff, all the machinery evaporates at runtime. It disappears. Runtime is pure instinct, or to be precise, runtime is once comp time has structured a bunch of things, at runtime, types don't exist anymore. You just have bytes and you have offsets and you have instructions that operate on these bytes and offsets. And so if you don't have like any debugging info, you don't know something what exactly is unless you start reasoning about it. And because that's how computers kind of work. So maybe the error message can be improved. It's a bit confusing. It's assuming that what I'm trying to do is create a comp time int, but then I'm trying to mutate it to use it in a wrong way. But my intention in that case wasn't at all to do a comp time thing. But anyway, I'm sure in the future this stuff can be improved. And now you know. If you watch this presentation, you know that if you get that error, sometimes it's because you forgot to specify how big your integer should be. And going back to the runtime versus comp time thing, you have to specify the size, because everything has to have a specified size, and that's how then everything works. Everything can tie together at runtime. So let's talk about runtime integer sizes, because there are some interesting things in there. So first of all, in Zig, you can type your own integers. So you can use I or U if you want a signed or an unsigned integer, and then you can write after that the number of bits you want your number, your variable to occupy. So I8, U16, but you can also come up with different numbers like U75. It's fine, and it's very useful. Like in other languages, there's just a few of those specified as keywords or whatever, and that's all you have. While here you can go also up to 65K, I believe, and that's like a current limitation that might not even be there in the future. Anyway, the number is gigantic, 65K bits. That's way too much for most people. But it's nice that you can type them down, and the language understands them that way, which is super cool. No top secret header file that you have to import with the right types like some other languages. There's also usize, isize. There's also a bunch of C underscore something types. Usize, I think it's the size of a pointer, and like the TLDR for people that don't know about too much about details and only program on like boring architectures. It's either 32-bit or 64-bit. 32-bit on 32-bit machines, 64-bit on 64-bit machines. That's it. iSize, same, but it's signed. And then, as I said, C* for interoperability with C. What about floats? Floats are a bit more complicated. You have F16, 32, 64, 128. You could have an F33 in theory, but floats they're not as simple as integers, and I encourage you to look these up yourself. So this is like homework if you want to learn more. But long story short, these are the ones that you have built into language, at least until today. You can also program your own integers. You can use type info, you can use type, or more probably, you don't want to use the low-level APIs, but start just by taking a look at what's into std.meta. And in our case, since we are talking about integer numbers, there's std.meta.int, which allows you, let me see if I can use my pointer, pointer, thank you. Takes in two parameters, whether the type of number that you want to get should be signed, so either I or U, right? But here you can put true or false, and the number of bits it should be big. So you can type them, which is useful when you are programming yourself, but you can also program them, like you can specify them programmatically at comp time, which is also useful when you're writing generic code. Now, let's fix the code then. This is how a loop ends up working correctly. You have to specify the type, right? But in this case, I'm not using a U something like a U20, U64 type, but I'm making my own using std meta int. And in this case, so my int is a U4, basically, right? Unsigned, and then 4 bits. And if you run this, it runs, and it does what you expect, prints the numbers. But again, bit size is important. I'm sure people that are used to programming in Zig know this already. But for everybody else, like if you're coming from Python, you have to be careful. Don't try to be too stingy. So if you don't know, just make it usize, just make it U64, whatever. But if it's too many, it's fine. If it's too few, it's a problem. So here I'm making a change. I'm just using 3 bits, but 3 bits don't go up to 10, right? 3 bits only get you unsigned, only get you go from 0 to 7. They only allow 8 different types of stuff. So this is a problem. So now you run it, and when you run it, you get an error because this is since we are not specifying any other flag, running this compile makes a debug build, and the debug build notices that, whoops, we get to 7. As I said, it's from 0 to 7, and when we try to go one more, we wrap around, and it notices that we are overflowing. So, not good. So to recap, you can type your own custom ints, nice. You can program them using, I recommend to look into std.meta at first. That's also nice. And when it's comp time stuff, you don't have to specify the size because, as I said, comp time is it's more self-aware. It can look in the mirror and recognize itself almost. Now, if you are if you're new to Zig, that's it. You can go home. Congratulations. You go write your stuff. There's nothing else to see here. The world is a safe place. No evils hiding in the shadows. U0 doesn't exist, and it can hurt you. So have a good night. For you, the show ends here. For everybody else, can U0 hurt you? Does it exist? Well, it does, and it can be confusing. This is what's happening on Programming Circle Jerk right now. So people are debating whether you should allow a U0 type on your program in your programming language or not. And so this person is saying, well, honestly, it's an interesting debate. I'm not sure which side I stand on. But makes sense, but from a type theory perspective, but in a low-level language where you expect a data type to have any memory representation that you can take out and so on. So what are you doing? U0 is weird. Also, Programming Circle Jerk, people make edgy jokes about stuff. So they also say, oh, well, you need U0 in Zig to represent the number of Zig jobs. Well. I'll have you know, there's at least 2 people in the world that have a Zig job. So there's also this one. Temple OS, Holy C, has U0. Which side of the debate does that strengthen? Well, you decide. This one, by the way, it's my favorite. Anyway, these people are not the only ones that are finding U0 interesting and maybe confusing. If we go back to the development of Zig like a few years ago, also contributors had opinions on this stuff. So there was one person that was particularly against U0, and this person immediately said, well, U0 is a bug. It's like, this is like saying that we can measure the length of 0 with a 0 length ruler. And like the issue that says we should remove U0, this is not a proposal, this is a bug in the language. And they also immediately submitted a pull request for that, which was rejected by Andrew. Now, let's have an emergency meeting. Was Andrew right or wrong at rejecting the pull request? Well, in my opinion, he was actually right, and I think that PR was an impostor. But let me first solve this mystery with a degree of ease that how can I say? It's understandable that while you're doing stuff, while you are designing stuff, you are unsure about things and you want to think about them in detail. But hindsight is 2020, so this is the best year to do this kind of analysis. But what I mean to say is that it's easy right after the fact to come back and say, well, yeah, I think this was obviously the right choice. But so let me try to explain that very easily, and let's talk about sets. So let's start by talking about sets, but when I say sets, I don't mean like mathematical sets or whatever. I'm talking about like good old data structures. So how do you make a set in Zig? Well, the standard library has a hash map, which is one reasonable way of implementing a set, and it's a generic hash map. So you can also do there's a nice trick that you can use where you set the values to, so you can provide types for both keys and values, right? And if you say, well, my value types are void, boom, you have a set. Kind of like in Go, you kind of do the same with maps, but then you put like an empty struct, or I don't know, it's kind of clunky. It's the same idea, generally speaking. It's kind of clunky though. This is nicer. You say, well, I have no values, my values are void. And so this is the generic code. This is a simplified version of the code inside the generic hash map. And you can see that it's a function, takes k and v as any types. Actually, I think I got this wrong. I think they should be types. Ignore the any. Sorry, they should be just types. So you have k and v, and then inside there's the element type, so the elements inside your map, and they are the key is of type k, the values of type v. and there you have it. So when you end up specifying that you want, for example, a number set, you call the function, anything else, what you get is something like this. So you say, well, my keys are numbers, but the values are void, and so this field here inside the struct, this is valid Zig. This compiles. This works. Now, normally you don't just write down straight up void inside a field like it's a useless field. Well, most of the time, it almost doesn't make any sense. But this, as a result of a generic comp time thing, is absolutely reasonable. It's one of, I think, of the best powers that you get from comp time Zig. So this is something that I think people shouldn't find confusing. You can use hash maps as sets, just set values to void, and you're done. So if you think this is reasonable, then the answer is that U0 is void, but for numerical ranges. And let me try to show you an example. And this example is, so Andrew told me that actually this example already existed as a test. So if you go to Zig test, stage 1 behavior bit shifting, you'll find it. My version, it's even more simplified. And I originally was thinking of something about like a generic like IP system where you have subnet masks that can change or something like this. But actually, I think this example is much more easier to understand. And actually, since I have a database background, I mean, sharding, man, do I love sharding. Again, not any type, just type. Sorry, this is a mistake in my slides. But here's the idea. You have a map, but the map is somehow, for some reason, sharded. So stuff doesn't go all in one place, but it goes in multiple places. And you can decide, and maybe the number of possible shards that you want to have, you want to squeeze it in a point, or you want to do some stuff like that, like some bit fiddling with it. And so you want to know what is the maximum number of shards that you want to support, and you want that to be a power of 2. So what you do, you, for example, might take in another comp time argument, S, which is, let's say it's like the shard space, and then your element is, every element is gonna have a key, a value, and the shard it belongs to, maybe something. Again, it's a simplified example. It doesn't have to make practical sense the way it's implemented here. It's just a slide. But the idea is that this shard then, it's of type meta int false S. So if we say, for example, 5, it means that, or 3, let's go back to our previous example, right? We say S is 3. That means that we can have 8 shards from 0 to 7. But here's the point. Let's say that you also want to have a sharded map that can collapse into a non-sharded map. It's a map where you say, well, I want 0 shards. I don't want any shard. Okay, fine. Then that means that shard can be a U0. There are no shards. Boom, and you're done. So that field shard becomes a U0, which again, kind of like void. It's kind of weird if you try to hard code in a struct a U0 field. I mean, you can if you want, but maybe that's, I can't think of a useful example off the top of my head. But this example that you see here is perfectly reasonable. It's kind of like what we were doing earlier with void, and that's pretty much it. So let's answer some quick questions. Would Zig type system break without U0? I think not. I think you could use void. Like if U0 was forbidden, you could put void there, and like you just have an if expression, and if S that you're given is 0, then this becomes, instead of being a U something, becomes void. You can do that. So this still works. On the other hand, is 0 then so nice that you can always use it like any other U something and never think about it anymore? Oh, not exactly. I think it makes some things easier, but it doesn't like automatically solve everything, probably. Think about serialization. Or let me put it this way. Like when you think about serialization, for example, I think you can use it like any other U star if you think that bit representations can go from 0 bits to n bits or whatever. So you kind of have to think about it sometimes. Now, of course, but what if I create a U0 variable? Hmm. I still think that the example that I just showed is the most useful one, or like class of useful things you can do with U0. But yeah, what happens if you do this? Can you do this? Does it compile? What can you put there? To replace the question mark, can you put there 5, 10, 42? Well, you can put 0. This compiles. This works. Is this correct? Is this correct? Maybe I should give chat a little bit of time to think about this and decide whether this should be considered correct or not. Can you put, you're putting a 0 into a U0 thing. Does this work? Like, should this be like this? Well, first let's recap. Use U0 as a limit case when you're doing comp time stuff and you have a numeric range that you want to make variable. But still be on the lookout for situation where you kind of still might want to special case it. Like, for example, in the case of serialization, if you have a U0 field, do you want to write it down in the serialized file or omit it or what? Well, I think it depends actually on your use case. And that's all there is to it, really. Like, from a practical standpoint, in my opinion, this is all you have to care about. And this is where U0 can be useful for you. Everything else is just theory crafting. But now, let's go into the rant. Is this correct? I think it's the wrong question. If you start thinking in those terms, I think you risk getting yourself into the same mental state that some people got themselves into. So let's try to reframe this a little bit. I think it's a reasonable choice because it's useful. And by the way, all this stuff can be programmed in a different way, right? You can decide, like, when Andrew or whoever wrote that specific code can make a U0 variable work in different ways in the context. You can have everything, right? Sometimes you are constrained by certain rules, but you still have a lot of agency there. So another choice could be to have a U0 variable be equal to 1 always. Kind of weird, I think, but it's just to show how different possibilities are there. And again, I might be missing out on some small detail when you are implementing it, where maybe making U0 equal to 0 makes everything easier, and making it equal to 1 would make it more clunky, but whatever. Another option could be, well, you could not allow assignment to U0 variables. You could say, well, U0 is a type, but you can't assign anything to it ever. Kind of weird, maybe, but let's take inspiration from some friends that are super hot on type stuff. And, well, they have a empty enum. This enum doesn't have any case. And for them, what they do with that is that they have this result thing where basically your function returns a result it's a union, can either be error or okay, so it can represent failures. And sometimes you want to conform your function to that interface, but at the same time you can't fail. So how can you convey that there is no failure option for your function while still having to conform yourself to the result thing? Well, you say, well, my error type is infallible, so the point is it's never going to happen, and that's maybe useful for some humans, and I don't know, maybe it's useful also for the Rust compiler now. Can I say that this is the right choice in an absolute sense? This good design is an absolute sense? I have no idea. I don't know. But given what I know about their type system, it seems reasonable. It conveys some meaning. So why am I stressing this point so much? Well, the point is, theory is a tool for achieving better practical outcomes. At least when it comes to software engineering, emphasis on engineering. I'm sure that if you're a mathematician and you want to think about theory for aesthetic reasons, sure, no problem. But at least for us, if you forget that the theory is a tool for better practical outcomes, we're going to write lousy software. So, long story short, is assigning 0 to U0 correct? Again, not a good question. It's reasonable. It works. But let's say, again, I don't have not even remotely all the context that, for example, Andrew has on this issue. But let's say in a hypothetical future or alternative universe where everybody uses U0 and assign stuff to it and assign 0 to it and get confused that U0 behaves in weird ways. Maybe at that point you could make the choice of saying, well, you know what? Let's forbid people from assigning to it, and that's the end of it. So at least we prevent people from making that mistake. That would be also reasonable, I think. Now there might, as I said, there might be some minor or like consequences that I can't see. But this mindset is the right mindset to have when thinking about this stuff. So let me answer one final question, which I think is also interesting, which is still kind of theoretical, but interesting and still kind of useful to know. So how can a value be stored in 0 bits, right? U0 is 0 bits. How can you put 0 in there, right? Well, here's an interesting thing to think about, especially if you haven't learned much about information theory. There is a relationship between bits and probability, but to keep things simpler, let's just say between bits and possibilities. So when you say this is a U3 variable, you're saying that the universe, the set of things that I can describe is 8 separate things that you want to distinguish. And you know that to disambiguate between these 8 different possibilities, you need 3 bits. And 6, for example, is one of these 8. Now, when you say U0, you're kind of saying there's only one possibility. And so there's nothing to disambiguate. Or let me flip it around. Since 3 bits allow you to disambiguate between 8 different things, 0 bits don't allow you to disambiguate between any. So you can say there is only one possibility. Now, should that possibility be 0? That's reasonable in many ways. You can, if you search the relevant issue, you will find that if you look at powers of 2 and whatever else, math kind of makes that work nicely. But the point is, no bits, it means only one possibility. So, how should that one possibility map to other types? Well, that's up to you. And here's what I mean by that. If you look at this code, you see there is this while I minor than 10. So this 10, by virtue of being 10, means that there are at least 10 different things that this type has to discriminate between. So this is this is at least 4 bytes. Maybe more, we don't know, but at least it's 4. And 10 compared to a U3 doesn't make sense. A U3 doesn't have a concept of 10. These are different types. U3, U4, these are different types, but you are still making them in relation to one another. So it's up to you how you want to map them. Of course, the obvious choice is you align them, or another way of saying that would be you cast the U3 to U4, and we have a well-defined way of doing so, and it generally makes sense and it works well for us. Sure, absolutely. But that's what you're doing. Let me bring this back. How the one possibility should map to other types, it's up to you. So maybe other languages don't allow you to implicitly cast a U3 or have a U3 interact with a U4, and they want you to explicitly cast it first. So there are different ways that you can do this stuff, and it's always the explicit choice of somebody. So is that code broken? For example, this is the 3-bit version, right? The one that doesn't go up to 10. So is this code broken? I mean, if you ask a debug build, like the debug build Zig, it is. If you ask release fast Zig, not really, because it keeps working. Although in the case of Zig, there's this nice operator that means that when you want wraparound semantics, you have to be explicit about it. So yes, it's broken, but maybe in another language without that operator, it's not as broken. So again, the point is, it's how you want things to interact with one another. And theory helps you understand the consequences and the implications of setting something to something, but you still have a ton of agency. And you should not try to think of this in a religious way where everything has to match together to how math says it should be. It's a fool's errand. And actually, in that regard, if you like thinking in abstract terms, here's a recommendation. Check out this book. It's called Gödel, Escher, and Bach. From Douglas Hofstadter. I stumbled upon this book in my first year in university, and man, was I lucky. It really set for me the tone of how to think about this stuff and what to expect, what not to expect. And spoilers, I think this book is from the 80s, so it's spoilers on a 40-year-old book. This whole book, it's a very, very long story, but interesting. Don't get me wrong, I highly recommend it. I think it's kind of thick. I don't remember the number of pages, but it is kind of thick. And it's a long story just to explain the implications of one math theorem where one guy found out that it actually demonstrated that math in all formal systems are kind of broken, or more precisely incomplete. And so don't treat this stuff as a religion. It's not going to get you anywhere. That's the end. And after zero, there's nothing confusing in Zig at all. So everything else is super simple. And yeah, let's not talk about anything else, at least not today. So now, is there any question? So actually, let me see some of the comments that were sent in the meantime. Oh man. So there were a few yes, a few no to the should U0 be 0 question. Yeah, everyone has opinions. What about no return? No return doesn't exist, and it can't hurt you. So don't worry, I think. I don't know. What about no return? By the way, I'm not a compiler or program language developer, so everything that I'm saying from the perspective of somebody that uses stuff. But from the perspective of somebody that uses stuff, no return is another super simple idea. Yes, it kind of sounds confusing, but why is no return a return type? What does that mean? I think the answer is that if you have, for example, a function that should return a number, a function that should return a given type, and then inside you have a switch, and inside the switch you have like 3 branches, you want all 3 branches to return the same thing that the function has to return, right? Having one branch that returns a number, another branch that returns a struct, that doesn't work in the type system. So, so the type system has to make sure that all the return types make sense. But if one of the branches causes the program to crash because it sends an interrupt signal or whatever, or it flips a switch and burns your computer, then it doesn't matter what the return type is. And that's what no return is. I guess no return is a type that always matches with other types, because if you get down that path, it doesn't matter because the return type is not going to be part of the equation anymore. At least that's what I can gather from thinking about it logically as a user. I'm sure there's more to it, so you can ask Andrew about more nuanced implications. Yeah, at least that's one property, I would say. Since it's easily testable, right? Because if you have a switch in Zig and you have 2 cases that return the right type, but then the third case panics, you know the panic is going to blow everything up, and the panic is not going to return the expected type, so it returns a type that has to be compatible. Anyway, yeah, that's pretty much it. So since there doesn't seem to be any question, let me see. Two. Yeah. By the way, yeah, some people also described U0 as Zig's $1 billion mistake. Not the right way of thinking about stuff. Not recommended. Okay. I don't think we have any questions, so let me give a spoiler like last time for what I'm working on, and let's bring this show to an end. By the way, 30 minutes for the whole presentation. I'd say not bad. I hope I didn't go too fast. In case, let me know. But well, for the next showtime, I'm working on error, panic, or unreachable. Again, it's another talk for mostly for people that are starting with Zig or like not super experts. I found myself asking the question multiple times and getting it wrong, by the way. So I think that is going to be interesting for a few people. So I guess. And with me is going to be also Felix, Master Q, 32, who's going to talk about his programming language that he's working on. So that's going to be also another interesting talk. Thank you, everyone. And check out the newsletter. Check out YouTube. Also on Twitter, slap all the social buttons that you can find. And see you next time.
This is how we